Now let us try to understand how does the length of the line is going to affect flow of signal from the source to the load. And to simplify the analysis, I'm going to choose load as x equal to 0, right, which will make the source location as minus L. So by replacing x equal to 0 on the load side, we can see that the voltage and the load is going to be equal to V plus V minus. So here we are defining, and V plus and V minus are the traveling waves in the positive and negative direction at the load side. Similarly, we can define for the current. Z0 minus V minus by Z0. Two waves on the load side, and it looks like at the load side, the forward traveling wave in the positive x direction gets reflected and becomes a reverse traveling wave. So we can define a quantity called a reflection coefficient. Any point x along the line is a ratio of the two traveling waves. And the way we have defined x at x equal to 0, which is on the load side, gamma at 0, okay, load side, this is equal to V minus by V plus. Okay, so now if we write the equation for the voltage at the source end of the line, it becomes V at location minus L. This is at the source side, becomes equal to V plus e to the power plus gamma L plus V minus e to the power minus gamma L. This is just a change in variable. And similarly, we can also write the current at the source side as V plus by Z0 e to the power gamma L minus V minus by Z0 e to the power minus gamma L. So if we want to find out what is the looking in impedance from the source side Zin, it is nothing but ratio of this voltage and current. And this side is equal to divided by I minus L, which is V plus e to the power gamma L plus V minus e to the power minus gamma L divided by V plus by Z0 minus V minus by Z0 L. And we can simplify this expression by taking V plus e to the power gamma L, we can take as common. It becomes 1 plus V minus by V plus, which is same as the reflection coefficient at the load side. Let's call it gamma L power minus 2 gamma small gamma L divided by 1 minus capital gamma L to the power minus 2 small gamma L, and the Z0 comes in the numerator. Expression for the input impedance looking from the source side, we can see is also a function of length of the line. The reflection coefficient or the load, which in turn depends on the impedance of the load. Gamma, which is the property of the line. And the Z0, characteristic impedance, which is also property of the line. See that one practical issue which may come when dealing with a transmission line is that the input impedance becomes a function of length of the line. And many times, even though the load and the property of the line in terms of the characteristic impedance and the propagation constant can be controlled, the length of the line many times are not defined at the time of the design of the system. So depending on the use case, the length of the line may change. So this can become a problem when we are dealing with wireless system design. Here we can see that Zin depends on length of the transmission line. So if you want to make the impedance, let's say, independent of the length of the line, one way to do is by choosing this L to be small enough such that we can approximate this exponential to be almost 1. So that will happen when, say, minus 2 gamma L will approach 0. So when gamma L, okay, which is also equal to J beta L for the lossless transmission line case, y approaches 0, it implies the looking in impedance is equal to Z0 into 1 plus gamma L divided by 1 minus gamma L. So this is a very useful situation. But how to make this term J beta L tending to 0? So we can see that this J beta L, this beta L is nothing but the actual phase shift added by the transmission line in the path of either the forward traveling wave or the negative direction traveling wave. Okay, so this can be rewritten as 2 pi by lambda into L. So beta decides that the phase is going to accumulate by 2 pi. It is going to cover a distance equal to the wavelength of the signal on the line. So that's why we are going to get beta to be equal to 2 pi by lambda. If this part has to tend to 0, it implies length has to be much smaller than lambda, where the length of the line is much smaller than the wavelength of the signal which is present on the line. This is also called as electrically short line. And for electrically short line, the input impedance doesn't depend on the length of the line. And effectively, we are approximating the transmission line as a short circuit. Just to get an idea about whether it is practically possible or not, if we take frequency of the signal to be 1 gigahertz, it implies the lambda to be equal to 30 centimeter in the air and in a different material where the cable is separated by some other material instead of a free space area, we will find that it will have its own dielectric constant. So the dielectric constant will cause this wavelength on the transmission line to reduce. So let's say if the dielectric constant is around 4, this will turn out to be 15 centimeter. The conclusion is the length of the line to be assumed to be much smaller than lambda is not practical in most of the wireless system design where antenna may be placed away from the packaged radio. Okay. So this is not feasible where we can just ignore this term and then get an input impedance which is independent of the length of the line. The second case is, can we do something about then this term called this gamma L? If we can do something about this gamma L, again we can see that if this gamma L becomes 0, then the input impedance is independent of length of the line. So let us try to see that Zn is equal to Z0 1 plus gamma e power minus gamma L divided by 1 minus gamma L e power minus 2 small gamma L when capital gamma L is equal to 0. It implies looking at impedance from the source side is equal to the Z0. So what is the meaning of gamma L to be equal to 0? You can see that this gamma L is the ratio of V minus and V plus at the load side, and the load side we also know that let's say there is a termination of RL. This is V plus, V minus. Okay. We have transmission line like this. Then we know that the load will force voltage by current to be equal to RL, which is equal to V plus plus V minus divided by V plus minus V minus. And since the capital gamma L is already defined as V minus by V plus, so it implies gamma L to be equal to, okay, so here this divided by Z0. So gamma L becomes equal to RL minus Z0 divided by RL plus Z0. So we can see that the reflection coefficient at the load side depends on the load termination and the characteristic impedance of the transmission line. Now coming back to our objective, where we wanted to make gamma L equal to 0, we can see that if the load impedance becomes equal to the characteristic impedance of the line, then gamma L becomes 0, RL to be equal to Z0, gamma L becomes 0, and consequently Zn becomes equal to 0. This situation looks more practical compared to the earlier case where we wanted the line to be always electrically short, and such a scenario where the termination is equal to the characteristic impedance of the transmission line is also called as matched termination for the transmission line. It becomes equal to Z naught. Z in is equal to Z naught, where the transmission line has a characteristic impedance of Z naught. Directly write the phase constant beta. It has a length of L. So, irrespective of the length of the line, we are seeing the input impedance is always equal to Z naught. So this length can be in meters or hundreds of meters, doesn't matter. Input impedance doesn't change. And this greatly simplifies the wireless system design. And such a situation where the termination is equal to the characteristic impedance of the line, we can see that there is no reflection at the load side. So if we have V plus, V minus becomes exactly equal to 0. Okay, because gamma L is also equal to 0. So there is no reflection. As a result of which, at any point along the line, if we look at, there is only forward traveling wave, then there is no traveling wave going from load towards the source side. If we just look at the same case when the termination is not perfect, or termination is not equal to the characteristic impedance of the line, we'll see that the reflection is non-zero, and as a result of which, at any point along the line, if we have to observe the voltage amplitude may change depending on the phase of the two traveling waves. Okay, and since we have got two traveling waves traveling in the opposite direction, it gives rise to what is called a standing wave. RL is some impedance not equal to Z naught. So, yes, when RL is not equal to Z naught, to standing wave on the transmission line. And the consequence of standing wave is that if you measure the voltage and move along the line, the amplitude of voltage will keep on changing. And this can be measured with the help of the ratio of maximum to minimum amplitude of the voltage when we move along the line. This is also called as voltage standing wave ratio. We call it this Vmax divided by Vmin. This Vmax will be happening when V plus and the reverse traveling wave both are in phase. So their amplitudes will get added, whereas minimum will occur when their amplitudes will be opposite. So this is what we are going to get, equal to a positive number with a minimum value when this gamma L becomes 0. The minimum value is going to be 1. It means there is no standing wave on the line. And the maximum value will occur when gamma L magnitude equal to 1. In such a scenario, there will be a point along the line at which there will be nulls if you measure the voltage, whereas there will be point along the line where the magnitude is going to be double than the magnitude of the forward or backward traveling wave. So this VSWR we can find for various termination condition. We make a table for various cases. The case when RL is equal to, let's say, Z0, we know that gamma L becomes 0 and VSWR becomes 1. Whereas when the RL is, let's say, short circuit, so your gamma L becomes -1. This is going to give a VSWR of infinity. Similarly, when RL becomes open circuit, gamma L becomes +1 and VSWR again becomes infinite. This is the case when we don't get any standing wave. Here we get maximum. The standing waves are indirectly a measurement of how much of reflection is present on the line or how much of this RL is deviated from the characteristic impedance of the line.